All right. So here's where we were last time. I'm not going to review everything, but we've got a linear state space model driven by white noise. For control people, there'd be an input here as well, but we subtract that away and ignore that. And then we have observations, which are a linear function of the state plus white noise. And white noise, I mean white. It's an uncorrelated process with second moments. And we'd like the wide sense, the best linear estimator of x, given observations up to time k. So xk plus 1 given k. And we'd also like to get the covariance because we'd like to get uncertainty, how bad our estimate is. So this is huge, and this is pretty meaningless. Right? Well, okay, cool. And we, I said that there are two steps in constructing this. And I had a pretty, at least I thought it was pretty, yeah. So we want a recursive algorithm. So at time, given observations up to k minus 1, we've got our estimate of the state at time k, and then a new estimate comes in, yk, and then there's an information update. And that gives us the estimate of x hat k given k. All right. So the same definition, except for instead of a k plus 1, here we have k. All right. And then there's a time update. And both of these are pretty easy based on what we've done so far. I explained last time that this is trivial. Once you know this in one line. I'll remind you of that in a bit. And from going from this to this involves an innovations business. Okay, so let's just look at that. Let's look at that info update. So we know that, I'll remind you in a moment, about how when you have an estimate and you give it new information, you use the innovations to be able to easily update your estimate. So let's do that. So we need the innovations. Okay, so we've got our yk, and remember what the innovations is? We subtract off the past. Okay, so there it is. That's the definition of the innovation. And so that's the notation that's used in the book, except I'm always using uppercase symbols for random variables. It makes a clear distinction. I called I innovations in the lectures before. Okay, so the same symbol for the same thing. Different symbols for the same thing. So what is this monster here? It shouldn't be hard. Check it out. Okay, standard shorthand when you have a string of random variables like this, you write y1 to k or just y superscript k to mean the vector. And but I forgot something. That's too much information. Should be -1 there. And there should be -1 there. So what is that? So these h's aren't random, they're just matrices. So it comes outside. And what's the expectation, with a hat here, what's the White-sense expectation of yk given the past? Well, this is an uncorrelated sequence, all right? And the y's are just linear functions of the v's and w's. The v's in the past and w's, it doesn't matter. And we're assuming that v is uncorrelated with all of those random variables, okay? So if v is uncorrelated with that subspace, by definition, its conditional White-sense mean is 0, because the projection is already 0. So you can imagine how frustrated I was that I couldn't get to this last lecture. I mean, it's such a trivial thing. So what you get as the innovations is just the difference. And then if you plug in this, you just get hk times, oh, there's a transpose there, I forgot. Sorry about that. Sorry about that. There are so many mistakes in the book, and then I'm adding more mistakes. I'm sorry. He uses a transpose there. And so y is already has the same form with the noise added on. Cool. And so you see the innovations is a sum of a white sequence, which is the measurement noise. And this error sequence is also white. It's an uncorrelated sequence. So, and we know the innovations itself is a white sequence. That's, that's why we did it. Cool. So now we can do the information update. We know that we can relate oh, wait a second. Yeah. We can do this sort of thing. Right away. So what is it again, everybody? We have our innovation. So we have our new estimate of xk at time k is the old estimate plus an update in terms of the innovation. And so we put in a covariance of x k minus its mean. I'm terrified I'm going to make a mistake. It's just, it's just, this is prone to errors, it's just, yeah. Okay, so remember I put a bar there to just denote the mean. And so we do that, and that is it. And also we have something about the covariances as well. Remember, when we get more information, we reduce the covariance. So we have a covariance here of the error given data up to time k for xk plus 1. We can do the same thing here with k plus 1 instead of k. If you look at that covariance matrix, what you get is the new covariance is the old covariance minus the covariance of this monster here. And what's that? Well, it's the expectation of this times its transpose. And you see that everything's deterministic except for this random thing here. And what's the expectation of that squared? We have scalar observations here. It's the covariance. So these guys will cancel. So you'll get this and you'll get this times the covariance of this times this, and one of them will, one pair will cancel. And then you'll get this thing again. Okay, and if you'd like to write this a different way, it's just the covariance of y tilde k in the areas of x, but that's it. Okay, so redo check. If you take this random vector and multiply it by its transpose and take the expectation, you will get this. All right, all right. Okay, cool. So are we done? I guess we're almost done, because we've got this update here. And then we need to use that here in the temporal update, which I showed you last time, but I'll remind you. So the temporal update is to go from this to this, but it's obvious, right? It's sitting there in front of our faces. Okay, and then again, the WK is outside of the grasp of these guys. So the Y1s, the YKs are just functions of previous W's at a bunch of Y's, a bunch of V's. So that's orthogonal to anything there. Okay? Just go and look at the dynamics. These guys are uncorrelated. So what you get is this is Fk times the White's expectation of xk given the observations up to time k. That's exactly what we call that. And then you can go and plug this monster back in. So you plug this in, and you get something nice. And another thing that's nice, because what you're seeing there is the common gain. Yeah, so the k sub k is fk times this whole monster. So it's fk times this whole thing. Oh yeah. Aha. There's a little, this goes back to discussions we were having. I don't need the bar there, I needed it earlier. You'll see. There's no mistake, don't worry. What's a covariance? It's the expectation of that times that transpose. That's assumed to be a scalar, so there's no transpose. That's a constant. I didn't need to put it there. It's somewhere else where you have to worry about the constants. Okay, we worried about that earlier, so we don't need to do that. So actually, this This is true, but it's not necessary, so it's just that. Right. This is a zero mean process, so this times a constant as mean zero. Yep.
So why doesn't it matter?
No, zero mean. I mean, look at the definition. That's the definition, right? This is equal to this. And the expectation is linear. Forget that. that's just a vector. It's a number. And so the mean of that is 0. So that whole thing is 0. Okay? So yeah, it's just because if you go back and look at the definitions earlier, at some other point you have to subtract this off. And yeah. Okay, so anyway, that's cool. So that's the common gain. And the next step is to work out what all these monsters are. And I mean, shall we? I guess so. It's not that bad. I mean, what's what is this covariance, for example? So what is it? Equals a question mark. So you got to fool around a bit. I'm going to try to do this open loop because reading my notes is annoying. So let's figure out what this covariance is. And by the way, when you read, I mean, if you read the PDF version of these notes, there's a mistake in every single line. Sometimes he puts the k up here, which means all the data. That's a mistake. Sometimes he puts in noise here. That was a mistake. It's just that he didn't. It puts all of us to sleep to present this. It's so hard. It's not because we're geniuses. It's just that look at this. I mean, you're falling asleep. You know, as a professor, you like to present concepts. You don't like to present algebraic derivations. And so, you know, we're mortal. Okay, so let's see. I've got the xk times the y tilde k, which is sitting right here. Oh. Okay, cool. All right, so I've got that, and let's think about this. I've got xk times this innovations term. Xk, vk, are they related? It looks like they are. So so what you do is you play a little trick. Wait a second. I do need my cheat sheet. No, somebody else tell me what to do. How do you get rid of VK? How do you get rid of VK? How do you do it? How do you do it? How do you do it? Tell me, how do you do it? Why is xk correlated with VK?
Don't they assume something about like they're mutually independent?
And, oh yeah. I'm sorry. No. I mean, you have to look at the time indices carefully. No, nothing's independent. They're uncorrelated. No, it's just so you have to look very carefully at this. xk plus 1 gets a. Oh no! Excuse me. I'm thinking of feedback problem. I'm thinking of inputs. It's just the context. When you have feedback, you can shove your v's into your x's. So I went to another planet for a second of a control system. These guys, these v's have nothing. X doesn't know about this. X has no idea you're spying on it. So this noise is uncorrelated. Yes. So that's That's an assumption. Vk is orthogonal to every xk, future, past, all of it. I got scared there. So okay. So then we did that. Now this looks hard, but this is an error which is orthogonal to past data. So I can stick in some past data. And I'm going to blow your minds by doing two things at once. This is a dot product, and we know that A dot B equals B dot A. So I just reverse the order of taking dots. There should be a transpose here, though. Right? So A transpose B is equal to B transpose A. All right? All right. And this guy here, this error here, excuse me, this error here is orthogonal to that. So that dot product is 0, so I could sneak it in. And you see that looks familiar. Cool, so we're able to get the first term in the gain without much trouble. And then we have to look at the covariance as well. All right. So it's the covariance of this monster. All right. So basically, the covariance is just, these are all, these are zero mean random variables, so it's just the expectation of this random vector. I'm sorry, it's a scalar. We're taking scalar measurement, so it's just it's the expectation of this thing squared. All right, it's the second moment. These are scalar observations. Covariance for zero mean, it just means the second moment. And the vk is orthogonal to xk. We all agreed on that, all right? And vk is orthogonal to x hat k given k minus 1. That's the definition here. It's got the hats. That's x hat k given k minus 1. See? Because this guy is in the past, and vk is orthogonal to the past. Right? Cool, and this has a name. I'll do it if you like. No, this whole thing. The covariance of this has a name. Well, I'll do the same thing I did before. So I would write this squared, but that wouldn't be very informative. It's better to use the same trick I used before, that A transpose B is the same as B transpose A. All right, so this whole complicated thing I've written down is just this squared. I've just written it this times itself, right? And then you can see I can take the HK transpose out on the left, the HK out on the right, and what I'm left with is the same covariance matrix. And this is what we call an RK. We have a name for this, it was RK. And so what we've done?
Are the first two steps in those covariants and not expected?
What's that?
Covariance of xk given yk realizing covariance.
This is a cross covariance. Oh, wait.
This one. Covariance of xt. Yeah, that one. Is it equal to covariance of xt?
That's a, oh, it's all K. There's no T's here.
No. The,
What? I'm
what is
listening.
equal to the RHS?
XK. So y tilde K is that?
Is that expectation or you've written expectation? Isn't that covariance?
No. Expectation. The definition of expectation is the dot product. Yeah.
No, but you didn't.
Doesn't matter. What's that?
The covariance, like, later in the end you applied it, but, like, shouldn't that be just be covariance?
No. No, the definition of the covariance is I should normalize. I mean, if you're worried about my normalization, right, I could put that in, but this is zero mean, so it doesn't matter. You know, but the definition of covariance is I take this, subtract off its mean, take this and subtract off its mean, but its mean 0.
The only confusion is because of the third step, you've written xk minus xk.
Well, no, what I left out was the x bar k, which I'm justified in doing because, because no, it's good. Because this is zero mean, it doesn't matter, okay? And then I slipped in not the mean, but the conditional mean. And I did that for different reasons. I'm allowed to sneak that in because it's orthogonal to these guys. The same reason I was able to get rid of this. I did a substitution. I replaced the mean by the conditional mean. And I could have, replaced it by 0. Anything I want. I can do whatever I want as long as it's orthogonal to this stuff. Yeah. No, that's good. All right, cool. So what's missing, everybody? So we've got the common gain. Involves this term here, which we have a very pretty formula for. It has this term here, which we have a very pretty similar formula for. What's missing?
Controller.
What?
The controller.
Nah, this is a control course. And what's missing? How would you code this up?
Do we have the transpose?
Oh, probably. Where? No, I mean, here? No, why scalar? I mean, I'm taking scalar measurements.
Okay.
Yeah, so I don't have a transpose here. You know, it would just, vector measurements are trivial, you just have to keep transposes everywhere. So it's just a bit more annoying. Okay, no, this is all good. Now come on, what's missing? Actually, one of my goals at the beginning, look at the beginning of your notes. My goal was to come up with this, which requires an algorithm and the covariance. So
Figure out the state at the current time step. That's what
I just did it.
The goal is. Yeah.
No, I had two goals. So you're right. One goal was to come up with this. I want to write code for that. And two is also was the covariance. And I'm missing that. And I need it not just because I want to have uncertainty bounds, but it appears everywhere. It's like the common gain depends on it. So unfortunately, we have to do that. Let's do it. But thank God I didn't erase that. Well, I guess it is there, isn't it? Hold on a second. So Yeah, so I've got this in terms of this. Plug it in and do it. So, is that right? Looks like it. All right, so it looks like it's got an error in there. And orthogonal, or maybe not. Should I not have done that? Let's see. Yeah, WK is definitely orthogonal to all this junk, and orthogonal to this junk. Everything's orthogonal. This is what I remember. Is that really correct? The three terms? Well, it's a big, complicated mess, and let's just do it. So everything here is orthogonal, right? Because WK was new noise, and it's orthogonal to all the past XKs and everything else. And WK is orthogonal to anything involving observation, so that's all gone. And now hold on a second. No. No, I don't want to do that. I don't like this, everybody. Do you? It's true. But let's make things easy on ourselves. This is true, but let's remember how simple this is in terms of the past. I'm expanding things out when I would end up contracting them again. All right? We just said that this is just fkx hat k given k. And so this is equal to the covariance, then, like I said before, do the same thing. And I want to keep this here, okay? So I'm going to get an fk times the error. And then the wk's are orthogonal to everything in sight. So I'm going to get an fk sigma k given k fk transpose. That's what's going to happen when I look at the covariance of the fk times the error. And then I get the covariance of wk, which is what we called qk. Okay, the covariance of wk is qk. That's what we define. And then you take this monster and you stick it in there, and you get this horrific recursive equation. for the covariance. Applause. I think I had 10% less typos than Bruce did, and he could sit by computer. All right. So anyway, there it is. You just take this. You know, you don't need that. But and we have formulas for each of these guys in terms of the sigmas, and so it all goes in. It's so it's a very, very nonlinear equation, but it works. Okay. All right. So you can code this baby up, and it's easy to do. All right. Questions? Is that clear?
Well, can you like maybe summarize like the impact it's had?
Oh my God, it's everywhere. Here's thank you very much. Here's the thing about this. I mean, nothing's linear, as I always joke. F is not equal to ma. Give me an example. And if you take a controls course, you're told friction is linear. Have you ever pushed on an iPad on a podium? I'm pushing it. Do you know that? It's not moving. Linear is so damn nonlinear. Friction is so damn nonlinear, it's awful. I mean, it's just it makes mechanical engineering a subject I would never want to study. Just kidding. That was just for you. But we use it anyway because nothing else works. It's just incredible how we take a nonlinear system and we try to apply optimal filters, and often they just don't work at all. So you basically, there are all sorts of tricks to use this in aerospace, target tracking, weather. I mean, they use this for weather forecasting. And guess what the dimension of X is? Where's X? You know, it's millions. And so they're propagating a covariance matrix, which is like a million by million, you know. And they have all sorts of clever tricks to do this. So it's like the way of estimating states in dynamical systems, like in prediction, like the weather, and yeah.